In the last video, we talked about two simple mechanisms. One is the simple reversible mechanism, so that's A goes to B in both directions, first order in both directions. And then we also talked about the sequential mechanism. Again, two first order steps, but in a row instead of back and forth. Later, we're going to talk about a third basic simple mechanism called the branch mechanism. That's this one, where A goes to do two different products. But before we do that, it makes sense at this point to talk about this thing called the steady state approximation. And also we're going to talk about the rate limiting step. And the reason it makes sense to talk about those now is because they both already came up when we were talking about the sequential mechanism. And the sequential mechanism illustrates them well. So let's talk about them. So let's suppose that you have something like this sequential mechanism we just talked about. A goes to I goes to P. And let's suppose that this second step is the fast one. We looked at that case up above. That means that every time a new I molecule is created, right away it goes to P, which means that its concentration never gets very high. That's this third case here, where the second step was 10 times faster than the first step. In that case, we can say, as I pointed out before, that the slope of the curve here never gets very high. Because the concentration itself never gets very high, the rate of change for the concentration also can't be very high, which means we can make the approximation, a decent approximation, at least a way of qualitatively understanding what's going on, that the rate of change for the intermediate is equal to 0, and that holds even if there are many intermediates. Let's suppose I have A goes to I1, goes to I2, goes to I3, and finally goes to P. So now we've got three different intermediates. Well, if everything is fast through here, if all these intermediates have fast rate constants for their own destruction, then none of these concentrations is going to get very high. All of the rates of change for those intermediates is going to be small. We can set all their rates of change equal to 0. And the overall reaction A goes to P will tend to look as if these intermediates aren't there or other more complicated things, which is what the steady state approximation is about. What is the behavior? What we're trying to basically answer with the steady state approximation is what's the rate of change or of the rate of production of the final product after a chain of reactions with many intermediates. So what's this rate of change for P? Now, there is a fundamental reason why the steady state approximation tends to work a lot of the time. And I pointed that out before when we were talking about, for example, the mechanism for the formation of water. Although in that case there were intermediates like O, a single isolated oxygen atom, a single hydrogen atom, and then this radical OH. All of those tend to follow this pattern. The steady state approximation works well for that mechanism, because all of these are extremely reactive, which means that the first collision they make after being created is likely to result in another reaction that destroys the intermediate. And so the reason that these intermediates tend to be in low concentration and that the rate away from the intermediate that destroys the intermediate is fast is because they're usually reactive. The first thing, maybe not the first collision destroys them, but they have a high probability of being destroyed on every collision. And so it doesn't take too many collisions before they're gone. All right, so what are the consequences then? If we're going to make this approximation, if we're going to say that all the intermediates have a rate of change that's 0, what can we do with that? And here's the answer. Let's look at our three-step sequential, or two-step, three-species sequential mechanism again, and let's set the rate of change for I, the intermediate, to be 0. So we've done that here. Then coming down here, we see that that means, because we have this rate law here, that K1 times A minus K2 times I has to be 0. And that means the intermediate concentration is K1 over K2 times the A concentration. In other words, it means it gives us a relationship that we can use to eliminate this intermediate concentration from consideration. We have now the intermediate concentration expressed as a function at all times of the concentration of A. And so, for example, if we want to look at the rate of production of P, that's K2 times I, as written from the mechanism itself. But now we have that I is equal to K1 over K2 times A, and so plugging that in, we get that the rate of production of P is just K1 times A. And that's now an overall rate law, not for any one step in the mechanism, but for the overall reaction A goes to P. And so the steady state mechanism has allowed us to eliminate the bothersome concentrations of intermediates which may not be measurable or even observable. Sometimes these intermediates have very, very low concentrations, very hard to detect. They're very transient in their existence at all. But using the steady state approximation, we can get rid of those bothersome things and have a rate law that depends only on the majority species, concentrations of the majority species. And so in this case, what that means is that the rate of change for A is approximately just an exponential decay. Again, A disappears as if the other reaction weren't present in this sequential mechanism. But the rate of formation for P, which up above was pretty complicated. Let's look at it up above. Here's the exact solution. Gotta find it. There it is. That's the exact solution that we got before. Now we're setting this to be a very low value at all points. Notice this hasn't changed. The way A behaves with time is still unchanged because it doesn't depend on what happens afterwards. But the rate of appearance for P is now a much simpler thing. If we go back down, here it is. Here it is now. It's just the same as if this were the whole, as if the mechanism didn't have any, as if this were elementary in its own right, actually. Behaves as if it were elementary, even though it's not. And so you get this essentially exponential rise and this exponential decay for A and P after a little bit of transient, right? Right at the beginning of the reaction, P behaves differently. It's got this flat region again because there is an intermediate. That's characteristic of the presence of an intermediate. And the behavior of A, it isn't as obvious, but the behavior of A is also not truly the way you'd expect things to be for a single reaction. But after that transient, then it becomes very close to a simple first-order decay. First-order buildup for P, first-order decay for A. Let's look at an example then, somewhat slightly more complicated example. So in this case, this is a made-up example, obviously, not real molecules or species, but all right, symbols still works. So we've got some molecule A2, reacts with 2 of something called B to give us 2 AB molecules. We say that the mechanism is A2 reacts with a B and the B steals an A from the A2 to form 1 AB plus a leftover A. And then the A collides with a single B to produce a second AB molecule, and that of course produces both of the 2 ABs in this overall reaction. That's a reasonable mechanism. It's kind of reminiscent, in fact, of the water-forming mechanism, the 4-step water-forming mechanism that we talked about earlier. It's a simpler one, simpler version of the same kind of thing. Well, in this case, the intermediate is this reactive A molecule, right? It's like as if it were if this were H2, then this would be a loose H atom. If this were O2, this would be a loose O atom, and so on. And so likely to be reactive. And so we are going to, what we're after is the rate of formation for this AB molecule given this mechanism for this overall chemical reaction. And if we just write down what the rate of change of AB would be from the mechanism without any approximations, we would get that from this step 1 here, we'd get K1 times A2 times B. And from step 2, with a plus sign, right, because it's formed, because it's a product, from step 2, we'd get K2 times A times B, again with a plus sign, because AB is a product. But the problem with that, I mean, there's nothing wrong with it in principle, but from a practical point of view, the problem with it is that it depends on the concentration of this intermediate A. And we may not have any way of measuring that intermediate A. And anyway, it's kind of a little bit more complicated than we'd like. Can we simplify it? Can we get rid of that intermediate? Well, let's see what the steady state approximation can do for us. The rate of change, the rate equation for A itself, again, looking at the mechanism, is one contribution. A is created here from the first step. Again, it's a plus sign because it's a product, times K1 times A2 times B. K1 times A2 times B. Minus now, because in the second step A is a reactant, so it's going away, so minus K2 times A times B. And so that's the rate equation for the intermediate A. We set that equal to 0 approximately, and that gives us that this quantity K2 times A times B is approximately equal to K1 times A2 times B. Well, K2 times A times B is the troublesome term in the rate of production for the product AB. And so we can just replace this thing with this in the rate law, and then we notice that that new term is exactly the same as the first term, and so we just get that the overall rate of formation of AB is 2 rather than a 1. We get a 2 times K1 times A2 times B. And now A2 and B are both majority species. There aren't any intermediates present anymore. And so we have, yes, a quote-unquote good overall rate law. All right, that's an illustration of the steady state approximation. Homework problems and so on will make use of the steady state approximation. And in fact, there are fairly complicated mechanisms that can be analyzed using the steady state approximation. We may, depending on how much time we have, we may look at some of those. But I think they'll be in the homework problems anyway. But let's move on then to the other type of, well, it's not really an approximation, it's a way of analyzing a mechanism called by looking at rate limiting steps. I think this idea is familiar to everybody already. It's usually taught in freshman chemistry. Let's suppose you have an overall reaction. So in this case, the overall reaction would be A goes to E. But it has it's a whole chain of steps, just like what we were talking about above, where you have a bunch of intermediates, B, C, and D, and whatever's in here. But one of the steps in the chain is really slow. So the fact that this is a chain of steps has the property that if I were to cut one of the steps, so if this K3, for example, were equal to 0, then we would stop the whole reaction, right? You could get to C, but you would never get beyond that. So everything, all the A's would turn into C's, and all the population would build up on C behind this dead step, this cut step. But you could never get further and go on to the product E. On the other hand, let's suppose you don't actually cut it. Let's suppose you just make K3 be quite small, so that step is slow rather than completely blocked. In that case, things will still have a tendency to build up on C, and then slowly they'll go on, they'll drain away to D, but since D is being created now in amounts that are small, and presumably K4 and steps beyond are all faster, that's what it means to say this is the slow step. It's the slowest step in the chain, so all these other late guys are faster. That means the D concentration and anything else that's in here will never build up very high. And furthermore, if you look at the overall rate at which you go from A to E, it's going to be dominated by this one slow step, right? All these steps are faster, so we get to C pretty fast in little time. Once we get to D, we get to E pretty fast in little time, but we take our time going from C to D. And so the overall time that it takes to get from A to E is dominated. It isn't completely the same as the slow step, maybe, but it's pretty close to the slow step. It's not going to be, most of the time required is going to occur in that slow step, and the time required to complete all these other steps is short compared to that one step. All right, so if K3 is much, much less than all the others, then we can write, it becomes very simple, that the overall rate, the production of, in this case, E, is approximately equal to just K3 times whatever the concentration of C happens to be at that time. And so if we plot out what was going on with all the species in this reaction, you can see we're losing A, of course, building up on B maybe for a little bit, but probably the B concentration is low too. And then when we get to C, everything backs up, and so eventually all the A, almost all the A, gets converted to C before it slowly starts leaking over to D. And in the meantime, once you get to D, yeah, all the concentrations after that are low, and eventually everything, because everything's irreversible in this case, you can't go backwards, everything has to eventually, ultimately end up on, piled up on E, and that's what eventually happens, but it takes a while, and the rate at which E appears is dominated by this one slow step. Right, so dE dt is equal to K3 times C. All right, so another example, this one from something biological, a little bit more interesting in its own right, because there are lots of biological reactions, biological pathways, if you like, or mechanisms that have a slow step in them. So in this case, it's in the mechanism for action of the DNA polymerase, of DNA polymerases generally. All DNA polymerases obey something like this mechanism. Some of these rate constants vary quite a bit from polymerase to polymerase because there's many different kinds of polymerases and they have different jobs, in fact. Not all of them are for replicating the genome. Some of them are for repair and other functions. But they all have a mechanism more or less like this. And what the mechanism says is the following. So here's the DNA. There's an enzyme, the DNA polymerase, DNAP, that binds at the junction where one strand of the DNA continues on and has bases that are going to be copied. And the second strand needs to be polymerized, and it needs to be polymerized in a way that every new incoming base that gets added is complementary to the base on the existing strand, what's called the template strand. And so how does that happen? How does the DNAP incorporate one single base? Well, the way it happens is the following. Here's the DNA polymerase, and I'm not going to write it out, but the DNA is bound to it, so this is really a DNA polymerase DNA complex. I didn't want to put the DNA in there too because then these names get even longer and more cumbersome than they already are. The DNAP complex binds a nucleoside triphosphate. That's one of the new incoming letters. It's like an ATP except that it's a deoxyribonucleotide rather than a ribonucleotide. And it can be either A or G or C or T. The N means A, G, C, or T. And it binds that NTP and then has that stuck on the molecule someplace, and then a conformational change takes place. And for those of you who know a little bit about DNA polymerases, what's happening is the DNA polymerase binds an NTP, and then it closes to form what's called a closed complex. It physically closes. There's a domain called the fingers that physically just closes like a hatch. And once the hatch is closed, then, and that's the slow step. So that closing step takes more time than any of the other steps in the cycle. Once it closes, however, then the chemical reaction takes place. It takes place pretty fast. Once the chemical reaction has taken place, now the new nucleotide has been added. And so what was an NTP, a raw nucleotide, gets turned into just a pyrophosphate. The rest of the nucleotide is now part of the DNA, and so it doesn't show up in this nomenclature I'm using. And then the next step is that the hatch opens again and releases. That's two steps. It opens and then releases a PI, or else it releases the pyrophosphate and then opens. Which order these two guys occur in varies from one to another, but in any case, the hatch opens and the pyrophosphate is released. That's the leftovers of the NTP gets released. And then you're back to where you started from, except now you've got an extra DNA letter in the growing DNA. And so this cycle continues, putting new letters into the DNA as it travels along. So that mechanism, I've written it as a cycle here, and it is a cycle. But it can also be written out as a line, just like what we talked about up above for rate-limiting steps. So just like, not that one. I think I erased it. It was in pink and I erased it. But anyway, just like up above, where this step, or this state right here is A, then it goes to this step, which is B, and so on, C, D, E, and then finally back to A prime. That's this step. I call it A prime because it's not quite the same thing, right? This one had a DNA with N letters on the growing strand. This one's got an extra letter on the growing strand, and so a letter has been added in going through this cycle. But this is more or less the same thing as A, except for the extra letter. It's the same thing as A. And so we can write, because this is the slow step. Even though this looks pretty complicated, and it is pretty complicated, lots of complicated things are going on in here, the overall rate of change for the formation of an extended DNA, for incorporating a new letter into the DNA, is just K2 times B here, where B is the concentration of this complex, the complex that exists right after the empty DNA polymerase DNA complex has bound a new NTP. All right, so we can analyze even this relatively complicated situation pretty well by just using the idea of a rate-limiting step. All right, that's the two approximations or two methods of analyzing a mechanism. Now let's turn to this third simple mechanism called the branch mechanism. I set up above what that is already. You have some molecule A, but that molecule can go away or turn into two different other molecules, B or C, with two different rate constants, K1 and K2. You can write that, this is written out as sort of a flow diagram, but you can also write it out more properly or more rigorously as a series of elementary steps. And in that case, it looks like this. A goes to B with rate constant K1, or A goes to C with rate constant K2. Both of these ways of writing things are equivalent. So yeah, the A is destroyed by two different possible paths. It goes away by two different possible paths, one that leads to B and one that leads to C. And it might make sense then, you might think that the rate at which A goes away is going to be something like the sum of the rate at which it goes by either path, right? If it goes away with rate K1 to B and with rate K2 to C, then overall it ought to go away with rate K1 plus K2, and that turns out to be the case. So I'll come back to this point. Down here, if we write the rate equations now, the rate of change for A, so remember our mechanism is this, A appears in both of the elementary steps, so there's 2 steps in its rate of change. One from this first step, so that's minus K1 times A. One from this second step, minus K2 times A. But A appears in both, of course, so you can factor it out, and it's just minus K1 plus K2 times A, which is a first-order decay, first-order mechanism decay with an effective rate constant. That's just the sum of both of the elementary rate constants. Then for the formation of B, it only appears in this first step, so dB dt is equal to K1 times A plus sign, because B is a product. And likewise, C only occurs in the second step, K2 times A. We also have the condition, as in the earlier cases, that A, the total of all 3 species has to be constant, right? Because those are all the possibilities. One of them is always just converting to one of the others. And so that the sum of all 3 concentrations has to be a constant. And we're going to say, as we have in all the other cases, that there isn't any B to start with and there isn't any C to start with. We're going to say everything starts with A, in which case this constant has to be the initial amount of A0, and that can never change. The total amount of stuff that's in the system can convert to different forms, A or B or C, but the total amount of stuff, which is just A0 here, can't change. All right, if we solve that properly, if we do the solutions to the differential equations again, we get a simple exponential decay for A, except that it's got this effective extra large rate constant, right, K1 plus K2, rather than just K1 or K2. And the buildup of B and C is 1 minus e to the minus K1 plus K2 in both cases. The only thing that differs between these two is this prefactor that's in front. And this is just an exponential rise. It's just an exponentially rising function. It's the same rise that you would get if there was only one step. So if it was just A goes to B, then you would get exactly this same behavior, this same exponential rise from B. All right, so what happens? Well, let's look at the ratio of these two. The ratio of B over C is equal to, well, if I divide this, all this stuff here, by all this stuff here, then all this later stuff is going to divide out, right? If I divide these two, all this latter stuff is going to divide out. Not only that, but this denominator here is going to divide out, and I'm just going to get K1 over K2. And this is true at all times. So the ratio of B to C is just the same thing as the ratio of our 2 rate constants, which means that not only is the rate of change of B and C controlled by these 2 rate constants, but the ratio of the total amount of B that we have over at any time to the amount of C that we have at any time is also controlled by the ratio of those 2 rate constants. And that gives rise to a graph that looks like this. The A just decays away exponentially, again with a decay constant that's K1 plus K2. And the 2 B's and the 2 other species, B and C, just rise exponentially, again with the decay constant, or rise constant in this case, K1 plus K2. But they do so in a way that if you wait long enough, when all the A has disappeared, and the reaction is basically stopped because you've reached completion, then you're going to have the ratio of B to C is controlled by these 2 rate constants, and also the sum of all those species. There's no A left at the end here, so that's 0. This is essentially a 0. That means the B and C concentrations have to add up to the total amount of A that was present at the beginning of the reaction. And so the overall picture is this. K1 and K2 determine how much B and C is created in the long term. K1 and K2 are basically controlling a switch. You've got or a valve, if you like. We've got a valve here and a valve here. And by changing the values of K1 and K2, we're determining how much of this stuff we get and how much of that stuff we get at the end. We're filling 2 pails through 2 hoses, and we've got valves on the hoses, and by turning up one valve or turning down the other one, we get, by the time we've run out of water in the source, we have more B if the first valve is wide open and less C. And on the other hand, if we do it the other way around, I got that backwards. That should be slow and that fast. So we open the valve on the second hose, then we get more C and less B. And you can see that in the formulas. I guess I won't go back up to them. It's pretty evident if you go look at those formulas that as the time gets long, then the concentration of B at, first of all, the concentration of A at infinity goes to 0. Concentration of B at time infinity goes to this quantity, and C goes to this quantity. Notice that these two guys are the same. In other words, B infinity over C infinity is just going to be equal to K1 over K2, of course, as it has to be, because all this other stuff they have in common and will divide out when you take the ratio. And so we can define the fraction of the total amount of stuff, which is A0 here, that ends up as B. That's just K1 over K1 plus K2, and likewise a fraction for C, K2 over K1 plus K2. Notice the B plus C is going to be equal to 1, so these are fractions. And in fact, the C concentration is equal to 1 minus B, so calculating B would allow you to calculate C as well, even without using this formula. And so let's look at a simple example. Let's suppose K1 is equal to 9 and K2 is equal to 1. That means that the top reaction here is 9 and the second reaction is 1, so the top reaction, the B reaction, is 9 times faster than the C reaction. Then the fraction of B will be K1, which is 9, divided by the sum, which is 9 plus 1, which is 10. So 90% of it ends up being B at the end at time infinity, and at every point along the way, too, actually. And likewise, it's 1 over 9 plus 1 for C, so only 1/10 of it ends up as C. All right, that is enough for today, I think.